Welcome to the Walton Pi. Today we are going to be talking about cardinality of sets. So to start off, let's define a few things involving sets. So a set is just a collection of objects, and an element is one of those objects in the set. So if we have the set of milk, eggs, flour, sugar, salt, butter, so maybe the recipes for bread or for cookies or something, that is a set because it is a collection of objects. Each of those objects, for example flour, are elements of the set. A subset of a set A is a sub-collection of objects where every element in the collection is an element of A. So back to our example of our set milk, eggs, flour, sugar, salt, and butter, the set of milk and eggs and sugar is a subset because every element in our new set, the set of milk, eggs, and sugar, is an element of our original set as well. So that's what makes it a subset. The power set of A is the set of all subsets of A. So if A is the set 1, 2, 3, the power set of A is going to be the set containing the empty set, the set containing 1, the set containing 2, and so on until we have the set containing 1, 2, and 3. Now, each of these sets is an object, and because it's an object, we are able to have those as elements of a set. So the power set of A is definitely going to be bigger than the set of A, but the question is, how much bigger? And that's what the cardinality is going to be able to tell us. So the cardinality of a set A, written with absolute value bars around the set, so absolute value of A, but it's read the cardinality of A, that measures the size of the set. So if A is a finite set, then the cardinality of A is the number of elements in the set. So back to here with A equals the set 1, 2, and 3, the cardinality of A is going to be 3 because there are 3 elements in A. But the cardinality of the power set of A is going to be the number of elements there. So there are going to be 8 elements, and you can go through and count all 8 of them if you would like. Though, then there are special characters that are going to represent the different sizes of infinity. Yes, you heard me right. There are multiple different sizes of infinity. I'll be talking about that in a future video. So, for example, if A is the set containing the letter A, the number 3, an umbrella, and oranges, then the cardinality of A is going to be 4. We can also look to see what the cardinality of an infinite set would be. So, if we look at the natural numbers, which is the set containing 0, 1, 2, 3, 4, 5, and so on, we can figure out pretty easily that the natural numbers are going to be infinite. So the cardinality of the natural numbers is not going to be a standard counting number. It's not going to be a finite value. Instead, the cardinality of the natural numbers is the definition for Aleph naught, which is this funny-looking N0 subscript, which is the smallest of our infinities. Well, again, I'll be talking about that in a future video. So if we have a finite set A, then the cardinality of the power set of A is going to be 2 raised to the cardinality of the set A. So if the cardinality of A is n, then the cardinality of the power set of A is going to be 2 to the n. Let's go through the proof of this together. This is going to be a proof by induction. So we need to start by establishing what our base case is. So we are going to start with the smallest possible set, namely the set with no elements, the empty set. So if A is the empty set, then it has no elements, and the only subset of the empty set is itself, the empty set. So that means the power set of the empty set is going to be the set containing the empty set. So there's only one element in the power set of A, which means that the cardinality of the power set of A is 1, which is the same thing as 2 to the 0. The next thing we have to do is we have to establish what is our inductive hypothesis. So this is going to be where we take any set B that has n elements. Then our assumption is that the cardinality of the power set of B is going to be 2 to the n. And that's going to be true no matter what set of n elements we choose. Our inductive step is going to be looking at any set with n plus 1 elements. Well, any set with n plus 1 elements can be written as a set with n elements plus an additional element. So the cardinality of A is going to be n plus 1, and now we have to show that the cardinality of the power set of A is going to be 2 to the n plus 1. So we start by noticing that every element in the power set of B is also going to be an element of the power set of A, because every subset of B is also a subset of A. So that means if C is an element of the power set of B, C union our additional element that makes A bigger than B is also going to be a subset of A, because we had a subset of B unioned with our extra element A, which means that that overall new set, C union the set containing A, is going to be a subset of our set A. So because we have now doubled the number of elements, because we can do that for every original element in the power set of B, we know that the cardinality of the power set of A is going to be 2 times 2 to the n, or 2 to the n plus 1. I hope this video was helpful to help you understand the idea of cardinalities. Please check out some of my other videos if you're interested in seeing what the cardinality of infinite sets are, and how we can show that two infinite sets actually have different cardinalities. Feel free to like and subscribe, it helps me out quite a bit. Check out some of my other videos, and good luck with all of your math.